Number 12, the graph of f is shown. Which of the following statements about f is false? The limit as x approaches a from the right of the function exists. Approaching a from the right, yep, we're heading somewhere. Where exactly? Who knows, but we're definitely heading to a specific value. That's good. That's true. How about as x approaches a from the left? Yep, we are definitely heading towards some value. That's true. Okay, so let's skip ahead for a second. We can see here that our arrows are going to touch. This is our finger test. They are going to touch. The limit from the left is equal to the limit from the right. So e, the limit in general, that will also exist. So let's give that one a true. Okay. Now we can head back to C. X equals a is in the domain of f. All right. Is there a point somewhere vertically where x is equal to a? So here's where x is equal to a. And yes, we certainly have a point there. That's true. So by the process of elimination, f is continuous at x equals a. That must be our false. And it's true. If we are moving right along, okay, we come to this spot, we have to take our pen up off the paper, put it back down, take it off again, put it back down, and continue on. The pen came off the paper. It's not continuous at the point where the pen came off the paper. Where did it come off the paper? At x equals a. D is our answer. Which of the following functions are continuous at x equals 1? All right. Well, again, if we're looking for continuity issues, we're looking for domain issues, for starters. That's the easiest thing to go after. Well, the domain of e to the x. Are there any spots where e to the x is going to have an issue? And the answer is no. Remember, we've drawn that one in the air. You can draw e to the x real easy. Right? And at no point did I have to take my pen off the paper. In fact, not only is that true for e to the x, that's true for all e's, including e to the x squared minus 1. Yeah, we got this x squared minus 1 right here. That's just going to move this graph around a little bit, but it's not going to change anything. It's still an e graph. This is not going to produce a 0 in the denominator. There is no denominator. There's no domain issues whatsoever. So 2 and 3 both check off as okay, right? Which means that those answers are out. So it's either 2 and 3 or 1, 2 and 3. Let's go to Roman numeral number 1, x squared minus 1. You can graph that. That's a polynomial. That's the graph of x squared moved 1 unit down. Did I have to take my pen off the paper at x equals 1? Absolutely not. Okay, there it is right there at that point. And my pen was staying on the paper. So that's true as well. So it's all 3. Our answer is E. Number 14. Which of the following functions are continuous for all real numbers x? Sine x. Yep. That's our wave function. No issues there. E to the x, we just talked about in the previous problem. That's always good. Tangent of x. We graph tangent of x. We are up and over, up and over. Got to keep taking our pen up off the paper. Now, testing strategies also tell us that 1 and 2 are true, and there's only one possibility that has 1 and 2. So obviously 3 is not, because there's no choice for 1, 2, and 3. But that being said, we can prove right here that tangent is not continuous for all real numbers. Finally, number 15, let f be this function right here. For what positive values of a is f continuous for all real numbers? In other words, can we plug in a value for a, and that will make x continuous for all real numbers? All right. And well, let's take a look at this. Continuity. We're interested in domain issues. And we will have a domain issue when we divide by 0. So, ultimately, the question is there a number that we can plug in here such that we don't have the ability to get a 0 in the denominator, given our choices, 1, 2, 4, or 1 and 4. So if we were to plug 1 in, we would have x squared minus 1. Okay. Can that be equal to 0? Yes, it can. It's equal to 0 at x equals 1 and negative 1. All right. So that's out, because we're looking for a value where x would not be able to be equal to 0. Okay. Let's go to x squared minus 2. If we have x squared minus 2, can that be equal to 0? Certainly. X squared would be equal to 2. We take the square root. X is equal to plus or minus the square root of 2. Okay, now it's an irrational number, but it's still an answer. Okay, that means basically that if x is equal to plus or minus the square root of 2, when a is 2, we would be dividing by 0. Well, that's how. So then we get to 4 only. If we have x squared minus 4, is that equal to 0? Well, yeah, x would be equal to 2 or negative 2. All right, so you're saying, well, wait a minute though. What if we put that 4 then there for a? All right, we're looking for values of a. If a is 4, we have a 4 right there. Don't these cross out? Well, yeah, they would. Okay, but all that tells us is that this function would behave like the function x minus 1. That's still, this denominator is still part of the function, which means the domain of this original function is what we're based off of. And if we have x squared minus 4 in the original function, then if x is 2 or negative 2, we've got an issue. So ultimately, none of these choices are possible. Okay. If there was a negative value for a, for example, if a was equal to negative 1, then our denominator would be x squared minus negative 1, or x squared plus 1. If our denominator is x squared plus 1, now there's no possible way to get a 0 in the denominator, and our function would be continuous for all real numbers, because this can't be factored to produce, there's no way to get 0. We're squaring a number, which means the lowest number that the result we get when we square a number is 0, right? 0 squared is 0. If we have negative 8 squared is 64. Then we're adding 1, so no matter what, we always get a positive value. So if there were negative values of a, that would be okay. But positive values of a, it's not possible.